As- Assalamualaikum students. Today we are going to continue with our chapter number 3, that is theories of covalent bonding and shapes of molecules. And in the previous lecture we have discussed hybridization, and we have also discussed sp3 hybridization, in which we have discussed some simple examples of sp3 hybridization, including a molecule with no lone pair, with one lone pair, and with two lone pairs. So let's continue with the topic of hybridization today.
Assalamualaikum students. In today's lecture, we will learn about molecular orbital theory. This theory is also related to the shapes of the molecules with having covalent bonding in them. Now, it includes the important aspects or the postulates of molecular orbital theory. Bond order will be discussed, and then its application for the homonuclear diatomic molecules will also be discussed with particular examples. Now, students, before we go to discuss the molecular orbital theory, we should know or you should be aware about the Western theory as well as BBT. Keep it in your minds that Western theory deals with the repulsion between that of the bonded and anti-bonded, or you say the lone pairs of electrons around the central metal atom. On the base of this repulsion, we predict the geometries or the shapes of the molecules. Then comes that of the VBT. VBT that explains the geometries or the shapes of the molecules on the base of the overlap of the atomic orbitals, which are partially filled, so that you can get a sigma bond formation or a pi bond formation, or the number of bonds between the two atoms which are being formed, that can be also known. Now, but there are certain limitations of this theory, that it is not going to explain the formation of the coordinate covalent bonds. It is not going to explain the formation of the odd electron molecules or the ions, or it is not explaining the paramagnetic behavior of oxygen molecule. Even it doesn't explain that whether the helium is going to form a molecule or not, why it is existing as a monoatomic system, right? So these all are answered by means of the molecular orbital theory. Let's have its little introduction. The theory was developed by Hewitt and Millikan in 1927 and 1928. Then further it was polished by Leonard and Jones in 1929. According to this theory, there is assumption that there is a linear combination of atomic orbitals. There is a linear combination of atomic orbitals to produce new one orbitals, which are termed as molecular orbital. Here it is, right? No more atomic orbitals you have to deal now. We are dealing now with the molecular orbitals. These molecular orbitals, they will surround the nuclei of both the bonded atoms, right? Now, these atomic orbitals, which when they are linearly combined or they overlap with each other, they will produce two types of the molecular orbitals, one with the low energy and the other one with the high energy. Those which have low energy, they are termed as bonding molecular orbitals, while those which have high energy, they are called anti-bonding molecular orbitals. Right? Now come to the next. Now, before we go to explain the molecular orbital diagrams of the different one examples or different molecules of homotype substances, let's have a look at how the orbitals overlap produces the molecular orbitals. Now, here it is given overlap of one s orbital of one atom with the 1s orbital of the second atom. For example, it is hydrogen atom, it is also a hydrogen atom. Here, you must remember that each orbital can have the capacity of only two electrons. This should be always in your mind, right? Now the overlap of these two, if you remember, S to S overlap will produce a sigma bond, if you remember, right? Here the two types of orbitals will be given by the linear overlap or linear combination of these two orbitals. Linear combination means here they will join like this on the central axis. They are linearly arranged, right? So their linear combination will give rise to types of the orbitals which are termed as the one which is present at the low energy. Here you can see the energy profile. It is rising in the upward direction. The lower one is termed as the bonding molecular orbital, and it is a sigma bonding molecular orbital, as the two orbitals, that is s orbitals, will overlap to produce a sigma bond, while higher above at the high energy it is anti-bonding molecular orbital, which is also termed as the sigma star, right? This is the difference between the sigma bond formed by the molecular orbitals and that of the anti-bonding molecular orbitals. The anti-bonding are represented by a steric bond formed on the type of the bond, right? So it is represented as sigma star. You can see the shape of the two orbitals. They are totally different from each other. The lower one orbitals are always more stable as compared to the orbitals which are at high energy, right? Here there is a nodal region present in. Now here it is given the molecular orbital theory applied on the two p orbitals. When two p orbitals which are of dumbbell shape, of the same shape and same energy of the two homo atoms, they join together, the regions which appear as bonding and anti-bonding regions, they are being mentioned here. Energy wise, the bonding molecular orbital formed by the overlap, that is the sideways overlap of the p orbital, they produce the pi bonds, which are termed as the pi bonding molecular orbitals, with having their complementary orbitals which are higher in energy, that are the anti-bonding molecular orbitals. As I told you earlier, there will also be the pi bonds with the star on it, as there is a difference between bonding and anti-bonding molecular orbital. You can see the difference in their shapes. Here in the higher region, there is existence of a nodal region between the two electronic clouds formed by the overlap of the two regions. According to physics, the overlap of the two orbitals to give the constructive interference produces the orbitals of the lower energy, which are much more stable, so they will occupy the electrons in them. Again, these molecular orbitals each have a capacity of 2 electrons in it, while the upper one or the higher energy orbitals, they are produced due to the destructive interference, right? So they will not undergo any of the occupation of electrons. Instead, up to we have the both of the orbitals which are completely filled, the atomic orbitals, then may they occupy the electrons in them. Okay, next one is the rules for the molecular orbitals filling. Here the molecular orbitals which are produced in the center, when the two atomic orbitals overlap, they follow all the rules as we have done for the filling of the atomic orbitals. For to write their electronic configuration, here the same rules are applied. If you remember Aufbau principle, Pauli's exclusion principle, and Hund's rule, according to Aufbau principle, orbitals will be filled according to the ascending mode of their energy. Then Pauli's exclusion principle says that no two electrons can have the same four quantum numbers. As I told you earlier, that one of the one of the electron will be with the clockwise spin, while the other one will be the anti-clockwise spin, so that a pair can be kept in an orbital with the opposite spin. There all the other quantum numbers will be same, but the quantum number spin will be different for both. The third one is Hertz's rule, that if the degenerate orbitals are available, so the filling will go on in such a way that they will be half filled first, and then they will occupy the 2 electrons in each further. Right, now this one is the rules which are being applied over there. The next one are the half of the orbitals which are produced by the overlap of the 2 orbitals will be the bonding molecular orbitals, and the half will be the anti-bonding. As I told you earlier that the bonding molecular orbitals are low in energy, and the occupation of electrons mostly occur in these bonding molecular orbitals, making sigma bonds or pi bonds, while the anti-bonding orbitals, which are of high energy, they mostly remain empty. Right? The difference between the energies of the atomic orbitals and the bonding molecular orbitals overlapping depends upon the extent of overlapping of the atomic orbitals. Right, now one thing more, that now here the molecular orbital diagram is given, that how it will be made and representing the different overlaps of the orbitals which will occur for the atomic orbitals of the two bonding atoms. Here it is given. Suppose if we want to give a molecular orbital diagram for hydrogen, so we will make up only this portion, this one, right? It shows the overlap of one hydrogen atom with the other hydrogen atom, 1s of one hydrogen and 1s of the other hydrogen will overlap with each other, and they will produce two regions. One is sigma bonding molecular orbital and the other one is the sigma star anti-bonding molecular orbital, as it is given here, right? But if we want to give for some higher element like that of lithium, the configuration of lithium is 1s2 and 2s1. It means not only 1s but 2s is also involved in bonding. So what I have to do, I have to draw this diagram first, and then I will draw another diagram for the 2s to 2s overlap. I have to show all the orbitals of the both atoms for overlapping, right? So first I will do the overlap of 1s and 1s of lithium, and then I will do the 2s and 2s overlap of the second orbit of the lithium, right? So I will make these two diagrams for these two up to this, right? For lithium I will draw these two. Okay, now here, as you can see that the orbital's energy is rising, so we are following above principle. You have to fill up the electrons given over there in these atomic orbitals into the central region only. सेंटर में आपको प्लेस करने हैं और कहीं नहीं आपने रखने, और वो भी 2 in each orbital, that 2 will be placed in each orbital, right? If I'm asked to draw the diagram for the higher orbit than this, the, for example, oxygen or fluorine or nitrogen, then what I will do, suppose if it is nitrogen, for nitrogen it is 1s2 2s2 and 2p3 as well. It means 1s of nitrogen 1 will overlap with 1s of nitrogen 2. I have to draw first this diagram, then I will draw this diagram as well, and then I will draw the third diagram which will come above these two, as that orbital is higher energy, that is 2p. Here these three places that represent the electrons in 2px, 2py and 2pz. It is from one side, that is atomic orbitals, and it is from the other side, that is, once again they are also the atomic orbitals of the other atom. They will overlap to give these formations of molecular orbital. For nitrogen, pi bonds will be formed first, and there will come the sigma bond. The two orbitals are degenerate, so they will follow Horn's rule. They will be filled first halfly and then completely, right? The upper three are the anti-bonding molecular orbitals formed in case of the, what you say, more than hydrogen present in that of the atom, so that they will occupy the anti-bonding molecular orbital after filling of the molecular orbital, right? So this is how to show molecular orbital diagrams from the different one elements. Right? Now come to the next one. Remember it. I have to draw how many diagrams for each substance. You have to remember it well. Right? For example, if we have done for only 1:1, that is for hydrogen. So now for each and every separately, I have to write a bond order for 1s, for 2s, for 2p. Not how? Bond order. Bond order tells you that how many bonds are possible between the two bonded atoms. Right? The overlap of the two of the orbitals will give rise how many bonds. For example, for hydrogen to hydrogen, as I told you earlier, there were present, let's say, look at the diagram first. This one is the diagram of, this is 1s of one hydrogen, this is 1s of the second hydrogen. Both have one electron in it. The arrangement is shown like this, that this one once again, the both of them were overlapped to produce a bonding molecular orbital and an anti-bonding molecular orbital. As there are two electrons, so place them as a pair in this lower energy orbital, the upper will remain empty. Now I will go into this equation, there it is given, or in this formula. Right? Bond order is followed like this. Number of electrons in BMOs. BMOs represents bonding molecular orbitals minus number of electrons in anti-bonding molecular orbitals divided by 2. As you can see in hydrogen, if the two electrons are present in molecular orbital that is lower in energy, that is BMO, so it will be 2 minus 0 upon 2. The value is 1. It means only one bond is formed between hydrogen atoms. Right? If I go for the lithium, then what happens next onward, you have to understand that what is given on the next one slides. Now here in this slide, relative energy levels of 2s and 2p are given. You can see the orbitals are arranged in ascending order of their energy as it is given. Now, the filling order of these orbitals are, for example, if we do for the molecular orbitals of oxygen, fluorine and neon, you know very well these are the molecular orbitals. On sides there are present atomic orbitals. These are atomic orbitals. Right? So the filling order is in accordance to the Avogadro principle as well as the Horn's rule or Pauli's exclusion principle. As I told you earlier, each orbital can have only two electrons. 2s and 2p, 2s overlap gives you sigma 2px, sigma 2s and sigma star 2s. Right? Sigma star will be filled after, before it will be filling of the sigma 2s. Then in the 2p orbitals, the filling order will be, the three orbitals will split into two types. One with a little bit low energy, that is sigma 2px lies down there, which is lower energy. Above there lies two degenerate orbitals, that is py and pz. Both of these will form pi bonds. In the higher one there is present pi star, and these belongs to the 2py and 2pz, while sigma 2px lies highest one. Right? Now this is the filling order of the molecular orbitals of oxygen, fluorine and neon. But if we go for the boron, carbon and nitrogen, अगर हमें इन्हें fill करना है orbitals में इनके electrons को, तो फिर देखें arrangement क्या difference आ रहा है. 2s, again we have to consider only the central one. These are the molecular orbitals. First filling will be there. Here 1s is not shown, but you have to give the 1s also, 1s will be 1s sigma will be filled first, and then sigma star will be filled secondly. Then there comes the sigma 2s will be filled next, and then sigma 2s steric one, which is filled further. Now there is a change in the diagram. Can you see? This is the part which differs. Now the two pi orbitals, they lie down there, and above is present the px, right? The pi orbitals will be formed first, and they will have the orbitals which are filled first, then that of the sigma 2px, right? Above portion is same. Again the pi star 2py and 2pz will be filled first, and then there comes the last one, that is sigma star 2px. The question is why there is such a difference. The answer lies in the reason that the energy difference between the 2s orbital of fluorine, oxygen or neon with that of the two p orbitals are too large. So there is no process of hybridization occurs. You know very well, in the process of hybridization, the two different energy orbitals, they become same in energy and same in shape after hybridization. So the energy of one orbital becomes lower while the other will become a little bit higher. This is what happened in the case of nitrogen, carbon and boron. This hybridization is not possible for oxygen, fluorine and neon, as it is given that the energy requirement is so high to transit from one level to another, that is it is 1595 kilojoules per mole for oxygen, and it is 2078 kilojoules for fluorine, while in case of the nitrogen, carbon and boron, where there occurs hybridization which makes the orbital arrangement change, px becomes higher in energy and 2s becomes lower in energy. You can see here, look at the difference, right? It lies above in case of this O2, F2 and Ne2. Okay, now here we have the energy for the requirement for the hybridization. It is only 554 kilojoules for boron. It is only 846 kilojoules for carbon, and it is only 1195 kilojoules for nitrogen. So it is quite low as compared to required for oxygen and fluorine. This is a very typical short question asked in questions that is short questions, that why there is a difference of diagram, or 2px is higher in energy in case of N2 or C2 or B2, why, as compared to that of O2, F2 and Ne2. So this is how the hybridization makes them to get higher in energy in case of nitrogen, carbon and boron, which is not possible in an oxygen, fluorine and neon. Come to this one. Here it is given what are the applications of the molecular orbital theory. The formation of the homonuclear diatomic molecules is given as next. Look at this molecule of hydrogen. The question is how you can say that there is present only one bond between two hydrogen atoms. So as it is given, you can see this is the atomic orbital of one hydrogen. This is the atomic orbital of second hydrogen. Each is carrying one electron in each. If we draw a general diagram, we will say two types of orbitals are formed: bonding molecular orbital and anti-bonding molecular orbital. I should remember that 1s to 1s overlap will give rise as sigma bond formation. So in the center there are present molecular orbitals. The first one is sigma 1s, and higher energy is the sigma star 1s. In total, I have only two electrons to be filled, so the lower energy orbital will be filled. First, the two electrons with the opposite spin will be accommodated here according to all the principles and the rules which we have learned before. So anti-bonding orbital will remain empty. Now you have to find out its bond order. Again, keep it in your minds. What is meant by bond order? Bond order, that how to calculate that how many bonds will be formed between the two bonded atoms. Here it is. Number of electrons in BMOs. BMO stands for bonding molecular orbitals of hydrogen. It is 2. Here it is. While in anti-bonding it is empty, nothing is present in it. Divided by 2, so it will comes out as 1. That it means hydrogen to hydrogen, one bond will be present. Right? Here the regions which will appear by the bonding and anti-bonding molecular orbitals, that is represented. You just have to draw this diagram. This formation of the orbital regions is just given to you for just recall or review, right? So what shapes appear. Otherwise, you just have to draw these molecular orbital diagrams, nothing else. Now, come to the next one. Here, the question is, helium exists monoatomic. Yet justify that helium do not make a molecule, right? Why not? It is explained by means of the molecular orbital theory. The atomic configuration for the helium is 1s2, means 2 electrons in each of the orbital. Once again, you have to draw the diagram for it. Again, we will start from the 1s overlap. Here the two atomic orbitals are given for helium. 1s for one helium and the 1s for the other helium. Each carry 2 electrons in it according to its capacity, right, with the opposite spin electrons present in it. So total number of electrons in atomic orbitals, it comes out 4, right? Each orbital in molecular bonding molecular orbital and anti-bonding, it has the capacity of only 2 electrons. I have to accommodate how many electrons? 4. So what I will do? I will place 2 electrons in sigma 1s and 2 in the next higher level, that is sigma star 1s. Right? So 4 electrons are accommodated in the molecular orbitals. Half of them are bonding and half of them are anti-bonding. Right? Now I have to take out bond order. This is the bond order mentioned. 2 electrons in bonding molecular orbital, while 2 electrons in anti-bonding molecular orbital divided by 2. The answer is 0. Means no bond formation between helium to helium will occur. Right? This is its configuration given with respect to the ascending order of the energy of the orbitals along with the configuration in it. So sigma 1s, which will occupy 2 electrons in it, is lower in energy, so you have to draw a sign like this. The higher one is sigma star 1s with 2 electrons in it in case of helium. It is the configuration which you will write for helium. This is how it is justified that no bond formation will occur between two helium atoms as the bond order is 0. Now the next two of the molecules are given. It is the formation of lithium 2, that is lithium molecule, and it is the formation of beryllium molecule. The configuration of lithium is 1s2 and 2s1, as it has 3 electrons in it, right? While for beryllium it is 1s2 and 2s2. Here it is given. These are also the homonuclear diatomic molecules, that lithium to lithium overlap and beryllium to beryllium overlap. Here you can see this is the diagram for 1s and this is the diagram of 2s. Same here, 1s, this is 1s and this is 2s. Right? You have to do the filling of the atomic orbitals with the number of electrons present in 1s of lithium. It is 2 in each. You have to fill the molecular orbitals. So what you will do, you will place 2 electrons in the lowest one and sigma orbital, and the 2 higher one in the further above one, that is the sigma star 1s, right? You can see the diagram is same just like that of helium. Okay, now take out its bond order separately. इतने portion का bond order अलग से निकालना, it will be 0, means no bond formation by the overlap of 1s to 1s. Okay, now come to the next one. Here in the above diagram, 2s is carrying 2 electrons, 1 in each. So when they will overlap, they will produce 2 regions, molecular orbitals and the antibonding molecular orbitals. There will be a sigma bond formation. The pair will occur or occupy the bonding molecular orbital, while other will stay empty. This is, now you have to find out the bond order for this as well. अब इसके लिए निकालें. When you will place it, what we'll do? Number of electrons in bonding molecular orbital minus number of electrons in anti-bonding molecular orbital. 2 minus 0 upon 2 will give rise 1 only. So one bond is possible between lithium to lithium. While in case of beryllium, there is present the, again, 4 electrons we have. 2 are present in 1s and 2 are present in 2s. The two diagrams will be similar. As you can see, the bond order between the two will also be 0, right? For 1s as well as for 2s, it will be 0. So we will say that no bond formation takes place between beryllium atoms, right? This is how to justify the formation and no formation of the bond to show its physical existence. Now this is all about today's lecture. The other slides or the other structures of the homonuclear diatomic molecules or their MOT diagrams will be discussed in the next one lecture. Allah Hafiz.